Welcome back. In our last lesson, we defined logic as the science of deciding what follows from what. With that in mind, let's go straight to our opening puzzle. What follows from these three statements? 1. Everyone who's sane can do logic. 2. No lunatics are fit to serve on a jury. And 3. None of your sons can do logic. This is an actual puzzle published by Lewis Carroll, who's better remembered as the author of the books Alice's Adventures in Wonderland and Through the Looking Glass. Lewis Carroll was actually his pen name. His real name was Charles Dodson, and under that name he was known as a very competent, if not extraordinary, mathematician. Near the end of the 19th century, he wrote 2 books on logic. One was called The Game of Logic, and the other was called Symbolic Logic. Today's lesson will explore some of the intriguing puzzles he presented and the scholarly reasons he had for presenting them. Let's go back to our opening puzzle. It's a bit much to try to tackle all 3 statements at once, so let's try taking them 2 at a time. We might make our lives simpler by taking statements 1 and 3 together. So, what follows from 1. Everyone who's sane can do logic, and 3. None of your sons can do logic? Well, if all sane people can do logic, but none of your sons can do logic, then we must conclude that none of your sons is sane. Now take that statement in conjunction with statement 2. No lunatics are fit to serve on a jury. I'm sure Carroll intended for us to understand lunatics to be the people who are not sane. So if none of your sons is sane, and if people who are not sane are not fit to serve on a jury, then the conclusion is that none of your sons is fit to serve on a jury. A nice little puzzle, and one that falls squarely within the confines of logic, since it's undoubtedly an instance of working out what follows from what. But it's nonetheless a bit different from the puzzles we considered in the last lesson. The type of sentences considered there involved what logicians refer to as propositions, which we can take to be the ordinary sorts of assertions that people make in normal conversation. We were also concerned with connectives such as and, or, and, if then. But the sentences in our opening puzzle, and the ones we'll consider in the puzzles to come, are much more narrow in their form. Abstractly, we're concerned with sentences of the form, all A's are B's, or no A's are B's, or perhaps some A's are B's. For example, the sentence, all cats are mammals is of this form, as is no cats are fish. Since these sentences involve relationships among categories of things, they are typically referred to as categorical propositions. Pairs of sentences of this sort can clearly impose logical burdens on those who hear them. If someone tells you that all cats are mammals, and then says all mammals are animals, would anyone hesitate to conclude that all cats are animals? If instead you hear all dogs are mammals, but no fish are mammals, would you not conclude that no dogs are fish? I think you would. Arguments of this sort, in which 2 categorical propositions lead unavoidably to a third, are referred to as categorical syllogisms. Their study was pioneered in antiquity by the Greek scholar Aristotle. Writing roughly in the 300s BCE, Aristotle wrote the first treatise in formal logic, at least that we know of. One accomplishment of this treatise was to classify all of the possible categorical syllogisms. After all, if categorical propositions can only take the forms I described above, then there are only so many ways they can be stacked up to form correct syllogisms. Since Aristotle pioneered the study of these arguments, it's common today to refer to their study as Aristotelian logic. The many, surprisingly subtle philosophical issues raised by such syllogisms were still a live concern for researchers in Lewis Carroll's time. His book, The Game of Logic, published in 1886, was meant to present the main ideas of this sort of logic in the form of a game suitable for children. The game in The Game of Logic was this. Carroll provided pairs of categorical statements, and the reader was challenged to figure out what they implied. That's it. That actually sounds more like homework than like a game, but it might help to keep in mind that, as in our opening example, Carroll's categorical statements were chosen to be absurd and humorous. It will also help to know that Carroll put forth a specific method for solving these puzzles that, at least to a certain personality type, could be considered fun. Later in this lesson, I'll give you a few examples to solve on your own, but it will help to work through some examples first. So here's the example that Carroll himself used to illustrate how the game is played. What would you conclude from these two statements? 1, no nice cakes are unwholesome, and 2, some new cakes are unwholesome. Now, before we continue, we should be clear about what sort of solution we're looking for. You'll notice that these statements are about cakes, and 3 different properties of them are mentioned. It would seem that cakes may or may not be nice, may or may not be new, and may or may not be wholesome. Now, wholesomeness appears in both statements, while niceness and newness appear once each. So the goal will be to eliminate the term appearing twice, thereby producing a statement relating the terms that appear once each. Now, this might seem strange right now, but it will seem much more natural after we work through an example. In Aristotelian logic, the term that appears twice in a syllogism is called the middle term. So Carroll used the letter M to represent it. In our puzzle, M represents wholesomeness. He then used X and Y to represent the other terms, so we will say that X represents niceness and Y represents newness. He then urged his readers to produce a diagram like this. We use the prime symbol to represent not having a property. So, if X represents being nice, then X prime represents not being nice. And if Y represents being new, then Y prime represents not being new. Now look carefully at the diagram. There are 8 regions corresponding to the 8 different combinations of nice or not nice, new or not new, and wholesome or not wholesome that we might have. The nice cakes live above the horizontal line, and the not nice cakes live below it. For newness or not newness, we look to the left or right of the vertical line. The wholesome cakes live inside the small square, while the unwholesome cakes live outside of it. Now let's revisit the first statement, 1, no nice cakes are unwholesome. Nice cakes live above the horizontal line. Unwholesome cakes live outside the small square. The regions answering to both descriptions are numbers 1 and 2, and the statement tells us those regions are empty. We'll represent this fact by placing gray counters in those regions like this. So, to review, nice cakes are found in the regions above the central horizontal line. Unwholesome cakes are found outside the central square. We use gray counters to indicate that a region is empty. Thus, if no nice cakes are unwholesome, it must be that regions 1 and 2 have nothing in them, and we place gray counters in those regions to represent that fact. Okay, the second premise is 2, some new cakes are unwholesome. The regions corresponding to being new and unwholesome are those to the left of the vertical line and outside the small square. In other words, regions 1 and 3. Statement 2 assures us there is at least one cake living in one of those regions. But we already know there are no cakes in region 1. If there were, then that cake would be both nice and unwholesome, and the first premise told us that such cakes are like unicorns. They don't exist. That means the new unwholesome cakes mentioned in premise 2 must live in region 3. We'll put a red counter in that region to represent that fact. So far, so good. But now what? Well, the goal was to come up with a statement that mentions only newness and niceness. The red counter in region 3 allows us to do just that. Region 3 corresponds to cakes that are new but not nice. So we can conclude that some new cakes are not nice. Problem solved. But let's look a bit more closely at those gray counters. Region 1 corresponds to cakes that are nice, new, and unwholesome. The first statement assured us that no cake was both nice and unwholesome. Can we also now conclude from the gray counter that no cakes are both nice and new? We cannot, because region 5 could contain cakes that are nice and new, and our statements do not tell us anything about that region. Likewise for the gray counter in region 2. It says there are no cakes that are nice, not new, and unwholesome, but there might still be nice but not new cakes in region 6. Okay, let's work through one more example to make sure we're all on the same page about how the game works. Here are your new statements. 1. All wasps are unfriendly. 2. All puppies are friendly. This time, we might define X to refer to being a puppy and Y to refer to being a wasp. Since friendliness is mentioned in both statements, it's the middle term and will therefore be represented with M. The region inside the small square represents friendliness, while the region outside the square refers to unfriendliness. Let's now fill in our diagram. Statement 1 says that all wasps are unfriendly. That's equivalent to saying no wasps are friendly. Friendly wasps, if there were such a thing, would be found in regions 5 and 7. Do you see why? It's because wasps are found in the regions to the left of the vertical line, and friendly things are found inside the central square. So these regions receive gray counters. Similarly, statement 2 implies that no puppies are unfriendly. Now, if there were unfriendly puppies, they would be found in regions 1 and 2, but since there are none, they receive gray counters as well. But there's actually more information to be had from our premises. After all, we know that puppies and wasps actually exist. That means there must be a red counter somewhere. But where? Well, let's see. The puppies are found above the central horizontal line in regions 1, 2, 5, and 6. But we already know that 3 of those regions are empty. That means we know that region 6 must have a red counter. And where do the wasps live? Well, wasps are found to the left of the vertical line in regions 1, 3, 5, and 7. But we already know that 3 of those regions are empty as well, and that means there must be a red counter in region 3. Now we look for a relationship between puppies and wasps that makes no mention of friendliness. As we've just noted, the red counter in region 3 allows us to conclude that some wasps are not puppies. And the red counter in region 6 allows us to draw the conclusion some puppies are not wasps. That's not bad, but I think we can do better. Look at the gray counters in regions 1 and 5. If there were anything that was both a wasp and a puppy, then it would be found in one of those regions. Since both of those regions are empty, we can conclude that no wasps are puppies. It's not the most surprising conclusion in the world, but it's nice to know it's certified by logic. You think you have the hang of it? Then maybe you'd enjoy working on a couple of puzzles taken from Carroll's book. Here's the first one. 1. Some eggs are hard-boiled, and 2. No eggs are uncrackable. Put me on pause and see if you can work it out. It's eggs that appear in both statements, so it's labeled M. We can then take X to represent things that are hard-boiled and Y to represent things that are crackable. Let's start filling in our diagram with no eggs are uncrackable. The eggs live inside the small square, and uncrackable things are found to the right of the vertical line. Those regions receive gray counters. The other premise says that some eggs are hard-boiled. Hard-boiled eggs are found inside the small square and above the horizontal line. But since one such region already has a gray counter, we see that the red counter must be placed in the other. Now we try to draw a conclusion. The gray counters don't help us much, but the red counter allows us to conclude some hard-boiled things are crackable. Okay, let's try one more. Here are your statements. 1. No monkeys are soldiers. 2. All monkeys are mischievous. Pause the video and see what you come up with. We'll do this one more quickly. The term appearing twice is monkeys, so that is labeled M. We let X represent soldiers and Y represent being something that's mischievous. With those definitions, we can represent our premises like this. This time, the red counter leads to the conclusion that some mischievous things are not soldiers. Let's switch gears now. Once you've considered puzzles involving two categorical premises, what's left but to consider more than two, just like in our opening puzzle? Let's try another one that involves three statements. 1. No ducks waltz. 2. No officers ever decline to waltz. And 3. All my poultry are ducks. What can we conclude? How might we go about this? Well, we could use the same method that we used for the opening puzzle, where we took the statements in pairs and drew intermediate conclusions from them. But what we'd really like is a more formal method. In other words, we don't just want to solve this problem, but would rather like to have a general procedure for solving any problems of this sort. I'll now show you one way of doing this, but I warn you in advance that I don't think this is an especially good way of going about things. Things are going to get a bit complicated for the next few minutes, and it will be just fine if you get the gist of what I'm saying without stopping to follow every detail. The method we'll consider follows naturally from what we've already done, so I think it's worth having a look. When we considered pairs of categorical statements, we used a certain sort of Venn diagram that was useful for representing the relationships among the terms involved. Could we do something like that for three categorical statements? Indeed, we can. First, let's translate our statements into symbolic language to make the relationships easier to follow. We can set x equal to ducks, y equal to my poultry, m equal to officers, and k equal to willing to waltz. With this notation, our statements become no x are k, then no m are not k, and finally all y are x. Here's a diagram we could use to represent the possible ways we can have or fail to have x, y, m, and k. Keep in mind that a prime next to the letter denotes failing to have that property. Now, notice that the diagram has 16 regions, which makes sense when you have 4 variables, each of which can have one of two values. Let's describe the various regions. Having or lacking x is shown by being above or below the horizontal line. Having or lacking y is shown by being to the left or right of the vertical line. Having or lacking m is shown by being inside or outside the horizontal inside rectangle. And having or lacking k is shown by being inside or outside the vertical inside rectangle. I must say that even though I don't endorse this method for solving the puzzle, I think it's very clever how Carroll came up with this diagram for representing relationships among 4 terms. Elsewhere in his writing, he even considered possible diagrams for 5 or 6 terms and beyond. We should also be clear on what sort of solution we're looking for. When dealing with 2 categorical statements, we said we wanted to eliminate the middle term. The analogous situation for more than 2 statements is that we want to eliminate any term that appears more than once. In this case, the terms k and x appear twice each, so our goal will be to have a conclusion that relates m to y. In other words, we want a conclusion that relates being an officer to being among my poultry. The pair of statements no x are k and no m are not k can now be represented like this. In other words, anything that was simultaneously x and k, or simultaneously m and not k, would be in one of those 8 regions. We use gray counters to make it clear that these regions are empty. The final premise was all y are x. Now, having y and lacking x is represented by the 4 regions below the horizontal line and to the left of the vertical line. One of these regions already has a gray counter, and this final premise tells us that the other 3 need gray counters as well. We can go a little further, though, since I think it's fair to assume that Carroll actually has some poultry. I don't think you make a statement like, all my poultry are ducks, when in fact you have no poultry at all. So we can assume that something that is both his poultry and is a duck actually exists, and the only place for such a thing to live is in the upper left corner. So our diagram now looks like this. You'll notice that some of the counters have been given an extra thick outline. These counters justify the conclusion that all y are not m. In other words, we get the conclusion all my poultry are not officers. Or, equivalently, the more reassuring, all officers are not among my poultry. Well, I told you it wasn't really the best way to go about this problem, but I do like the attitude behind this solution. What I mean by that is that it's always good to generalize your problem-solving strategies to the furthest extent possible. The method of using Venn diagrams worked very well for puzzles involving two statements. So it's natural to wonder if we can adapt the same method to handle more than two statements. We just saw that we can, but that the method becomes very cumbersome, even just for three statements. So it seems we should be looking for other methods, and Carroll had them. He devised a very clever algebraic procedure for expressing categorical statements entirely in symbolic form. Then, by carrying out certain specific steps, the answer would just sort of appear, as if by magic. He also developed a procedure for handling categorical statements that involved more than two terms, like all cats are furry animals, which involves the terms cats, furry, and animals. This method involved the construction of certain complex tree diagrams. I won't attempt to show you how these methods actually worked, but what's interesting about them is that, though Carroll illustrated them using the sorts of humorous puzzles we've seen so far, he intended his solution methods to represent a contribution to scholarship in this area. A problem that was of interest to logicians of the time was precisely to devise a formal procedure for solving the so-called elimination problem, meaning the problem of eliminating repeated terms in lists of categorical statements. Carroll's methods represented a solution to that problem, at least for certain sorts of lists. Carroll's puzzles are fun to read, even if you choose not to try to solve them yourself. So I'll offer two more that you can try to solve on your own, or you can just skip straight to the solutions if you prefer. First, here's another one that involves three premises. 1. Puppies that will not lie still are always grateful for the loan of a skipping rope. 2. A lame puppy would not say thank you if you offered to lend it a skipping rope. And 3. None but lame puppies ever care to do worsted work. Worsted work is a 19th century expression for knitting, if you were wondering. Now, what can you conclude from those premises? Okay, so we have our three statements on the screen. Looking at the first two statements, if puppies that will not lie still are grateful for a skipping rope, but lame puppies are not grateful for a skipping rope, then it must be that all lame puppies lie still. But if all lame puppies lie still, but only lame puppies ever care to do worsted work, then we conclude that puppies that will not lie still don't care to do worsted work. Carroll had a lot of fun devising and solving his puzzles. He even presented a puzzle with 50 premises. I'll spare you that monstrosity and just give you one with 7. As I've said, I think this is just fun to read. I definitely won't object if you decide to skip straight to the solution on this one, but you might enjoy solving it nevertheless. Here we go. 1. All the policemen on this beat sup with our cook. 2. No man with long hair can fail to be a poet. 3. Amos Judd has never been in prison. 4. Our cook's cousins all love cold mutton. 5. None but policemen on this beat are poets. 6. None but her cousins ever sup with our cook. And 7. Men with short hair have all been in prison. Now, I think you'll find that Amos Judd and loving cold mutton are the two singletons here. So try to come up with a statement that relates them. So what's the solution? Well, the solution is that Amos Judd loves cold mutton. I won't walk you through the steps, but if you want to try it yourself, I suggest looking for intermediate conclusions by taking the statements in the order 1, 5, 2, 6, 4, 7, and 3. We're almost out of time, so let's wrap this up. I have to confess, when I first read The Game of Logic, I found it to be a lot of fun. Carroll includes more than 50 puzzles for solving, and I duly made a Venn diagram, used pennies and nickels for counters, and worked out a fair number of them. And Carroll, recall, intended for the game to be played by children, so as to teach them fundamental ideas in logic. So I feel I must share with you an actual review of the book that appeared in a prominent magazine of the time called Literary World. I'll read you the bulk of the review, since I love the bluntness and sarcasm, even if I disagree with the sentiment. Here it is. We confess to having spent some minutes in trying to make out just how children are to be persuaded to enjoy Mr. Lewis Carroll's new book, The Game of Logic, with its accompanying diagrams and red and gray wafers. There may be young people capable of being amused by such syllogisms as no old rabbits are greedy, some not greedy rabbits are black, all white rabbits are free from greediness, and by disposing X and Y, predicates, attributes, major and minor premises in order due, with a red wafer here and two gray wafers there. But we should be at a loss where to lay our hands upon such young people. A sturdy boy would, we are inclined to think, spurn the game of logic as a stupid sham, black rabbits, greedy rabbits, pink pigs, and all, and clamor for some play that is really play, or else some study that is really study, on the principle that two things, each good in itself, often make, when mixed, a third thing which is neither good nor desirable. As a professional mathematician, I'm well accustomed to other people looking at me funny when they find out what I think is fun. But that's life. See you next time.